At 8 in the morning, the turbine hall feels more like a factory than the beating heart of one of the largest power plants on Earth. It is loud, but it is a familiar loud. The deep, steady hum of generators, the constant vibration underfoot that everyone has learned to stop noticing. Men and women in blue and gray coveralls move along the gallery, clipboards in hand, radios at their hips, trading quick jokes that vanish into the noise before they finish. Overhead, fluorescent lights flatten the space into long bands of white, reflecting off painted steel and damp concrete, turning the mist in the air into a faint, permanent haze. Outside, beyond the thick walls and the few narrow windows, Siberia is just waking up. Cool August air, low clouds over the Yenisei River, the dam's concrete face holding back a vast, invisible weight of water. Few people in the hall think about that water directly. They think instead about the shift schedule, the maintenance work still half finished, the pressure from the grid to keep megawatts flowing as factories and cities draw their morning power. On the control panels, numbers flicker and stabilize. Operators adjust settings with the relaxed precision that comes from years of repetition. Turbine units line the cavernous room in a row, each with its own personality. This one always a little hotter, that one known for a stubborn vibration that the mechanics have chased for months. Today, more people than usual are on the floor, drifting between machines, checking gauges, noting readings, trusting that the concrete beneath them is as unshakable as it looks. The hall is not quiet, but it is stable. There's a rhythm to it. Footsteps over metal grating, the distant crackle of a radio, the occasional clank of a tool against a railing. Somewhere below, unseen, steel blades spin in dark water under a head nearly 700 feet high, turning the river's fall into electricity. The people above feel only the softened echo of that violence as a constant tremor in the soles of their boots, a background presence that has become part of the building's character. If anyone glances at a shaking handrail or feels a desk buzz a little stronger than usual, they file it away with all the other quirks of an aging powerhouse and keep moving. It happens just after 8:13. The first sign is not a sight, but a feeling. A low, rising shudder that does not match the usual pulse of the machines. Coffee in mugs ripples, pens roll on clipboards. A few people pause mid-step, trying to decide whether this is anything at all. Then the sound reaches them. A single, impossibly loud crack that cuts through the machinery, sharp enough to make people duck instinctively, even before they understand what they are hearing. In the space of a heartbeat, the background noise of the plant is replaced by something raw and unfamiliar, as if the building itself had screamed. Near one of the turbine units, the floor seems to jump. A circular metal cover, the kind that usually sits flush and unmoving, erupts upward as if kicked from below by a giant. The mass of steel, weighing more than most houses, lifts into the air, tearing free from the bolts that have held it in place for decades. Beneath it, a spinning rotor follows, still turning, flinging spray as it rises, the invisible force of the river below driving it upward into the hall. In the seconds it takes gravity to notice, the rotor is already moving sideways, scything through walkways, machinery, and anything living in its path. People closest to the unit barely have time to register the motion. One moment they are standing on solid steel, the next they are in a storm of metal fragments, shattering glass and tearing cables. The air fills with the shriek of tortured metal and the heavy, wet thud of debris hitting walls and equipment. Somewhere, a man turns toward the noise and sees only a blur of spinning mass and white spray before the lights above him explode in a shower of glass. Another is thrown off his feet by a blast of air and water that slams into his chest like a physical wall. Then the water arrives. Without the turbine in its place, the open throat of the penstock connects the river's full pressure directly to the hall. A column of water erupts upward from the pit, not as a spray, but as a solid, surging mass, instantly drenching everything in its reach. It hits the ceiling and rebounds in chaotic sheets, knocking people off ladders, sweeping tools and bodies across the slick concrete. Within moments, the gleaming floor is gone. In its place is a rising, churning pool that climbs over boots and knees, hiding missing grates and jagged metal below the surface. The power dies almost as quickly. The lights flicker once, twice, then vanish, plunging the huge space into a dim, emergency-lit twilight where only a few red indicators and pale skylights offer any sense of direction. The reassuring hum of multiple generators collapses into a chaotic mix of grinding, slowing machinery, and sudden silence as units trip offline or are destroyed. In the half-dark, alarms wail from panels that are already shorting out, their warning tones blending with shouted names and panicked orders. The hall, which minutes ago had felt solid and permanent, now feels like the inside of a sinking ship. For those still standing, instinct takes over. Some run toward ladders and stairwells they can no longer see clearly, guided only by memory and the faint glow of exit signs. Others cling to railings as the current tugs at their legs. A technician, waist-deep in cold, rushing water, gropes along a wall for a familiar doorway, feeling broken tiles and hanging cables under his fingers. Every step risks a hidden hole, a live wire, a piece of twisted steel waiting beneath the opaque surface. Somewhere above, part of the roof gives way with a grinding roar, and a cloud of dust and fragments rains down into the already flooded hall. Outside the powerhouse, the change is visible, but not yet understood. Workers on the dam crest feel a faint vibration and turn toward the structure below, seeing only a plume of mist and dust rising from the turbine building. Radios crackle with partial messages. Unit 2, explosion, water in the hall, cut off by static and overlapping voices. Sirens begin to sound, first one, then several, their echoes chasing each other along the length of the dam and down toward the river. Farther away, in towns and factories across the region, lights blink and machines stall as the grid suddenly loses thousands of megawatts. But the people in those rooms have no idea yet what has happened at the dam. Inside, the disaster is not over. It is settling into a new, terrifying kind of normal. The water keeps coming, relentless, pouring through the ruined unit into the hall, then down into lower levels, filling control rooms and cable tunnels that were never meant to see the river's touch. Survivors cluster wherever they can find high ground, on stair landings, on machinery platforms, in cramped pockets of relative safety, soaked, shivering, and coughing in the damp, metallic air. They listen for voices over the roar, trying to answer calls, counting who is here and who is not, knowing only that the morning they walked into has been torn away in less than a minute. Outside, rescue is starting to mobilize, but for those trapped inside the dark, flooded powerhouse, the only reality is the cold water rising around their boots and the echo of that first impossible sound. The immediate horror of that morning has been recounted. The water has been pumped out. The bodies have been recovered. The emergency has passed into memory. What remains is a different kind of work. Understanding how this happened and ensuring that the 75 lives lost that day means something more than tragedy. This is not about blame. It is about learning. It is about the responsibility we carry when we build systems at this scale. The questions that follow are technical, yes, but they are also deeply human. They are about choices made under pressure, systems designed decades earlier, warnings that went unheeded, and the narrow space between acceptable risk and catastrophic failure. What follows is an examination of what went wrong, what we learned, and what changed because 75 people went to work on an ordinary Monday morning and never came home. At its core, the Sayano Shushenskaya disaster was a mechanical failure. The bolts holding the turbine cover in place broke, allowing 1,500 tons of spinning machinery to be violently expelled by water pressure. But that simple statement conceals layers of complexity about how we operate critical infrastructure at the edge of its design limits. Think of the turbine cover bolts like the lug nuts on a car wheel. They hold enormous forces in place through constant tension, but unlike lug nuts, these bolts were subjected to continuous vibration, immense pressure, and cyclic stress for 30 years. Metal fatigue is inevitable under these conditions. Microscopic cracks form and grow with each stress cycle, slowly weakening the material. The official investigation found that 41 of 49 recovered bolts had fatigue cracks. 8 bolts
had cracks through more than 90% of their cross-section, meaning they were barely holding on at all. At least 6 bolts were missing their securing nuts entirely, likely lost during decades of operation and inadequate maintenance. But the bolts did not fail randomly. They failed because turbine 2 was being operated in a way that dramatically accelerated the stress on already weakened components. Hydroelectric turbines are designed to operate efficiently within specific power ranges. Between about 40 and 60% of maximum power, they enter what engineers call a rough zone, a range where the water flow becomes turbulent and unstable, causing severe vibrations. Operating in this zone occasionally is unavoidable. Operating in it repeatedly all night long with a 30-year-old turbine showing vibration readings 4 times the safety limit is something else entirely. The night before the disaster, the Bratskaya power station fire forced Sayano Shushenskaya to take on grid frequency regulation duties, a job that required constant power adjustments. Turbine 2, despite its known vibration problems, was selected as the best available unit for this role. From midnight to 8 a.m., it cycled between 170 and 600 megawatts 6 times, passing through the rough zone with each transition. Each passage through the rough zone was like hitting a pothole at highway speed. Once or twice, your car can handle it. Do it hundreds of times with worn suspension components, and something will break. At 8:12 a.m., when the automatic control system reduced power one more time, the accumulated stress finally exceeded what the deteriorated bolts could withstand. When the bolts failed, 20 bars of water pressure, equivalent to the pressure 650 feet underwater, was suddenly released. The turbine rotor, weighing 160 tons and spinning at high speed, was driven upward by this pressure. It rose approximately 50 feet into the air, destroying the turbine hall roof and creating a massive breach through which 100,000 gallons of water per second began flooding the plant. The cascading failure that followed was not a design flaw, it was a catastrophic loss of control. With all electrical systems flooded and shorted, the automatic intake gates failed simultaneously. The automatic turbine governors, the monitoring systems, all depended on the same electrical infrastructure that was destroyed in the initial failure. Defense in depth means that safety systems should not share common failure modes. This lesson applies beyond hydropower, in nuclear plants, in chemical facilities, in aviation, anywhere that multiple systems are expected to provide redundant protection. True redundancy requires independence, not just duplication. The culture of operation played a clear role in why warnings were missed. Vibration readings had been climbing for months. The data existed, but Turbine 2 had recently been maintained and was thought to be the most reliable unit available despite being at the end of its design life. Economic pressures, the need to keep power flowing to Siberia's industries, meant that marginal equipment stayed in service when it should have been taken offline for thorough inspection and repair. But culture explains why the warnings were ignored. It does not explain what failed. What failed was metal, bolts that had reached the end of their fatigue life while being subjected to operational stresses they were never designed to endure repeatedly. The disaster at Sayano Shushenskaya taught the hydropower industry several lessons that extend far beyond this single plant. Design life ratings are not suggestions, they are warnings. A 30-year turbine operating at the end of its design life requires fundamentally different monitoring and operational constraints than a new machine. The assumption that recent maintenance makes aging equipment equivalent to new equipment is dangerous. Fatigue damage accumulates regardless of surface-level repairs, and high cycle stress on deteriorated components will find the weakest link. This lesson applies across hydropower infrastructure domains, power generation, bridges, aircraft, pressure vessels, any system where cyclic stress accumulates over time. Age must be treated as a fundamental constraint, not an administrative category. The plant's Soviet-era monitoring system could not detect the high-frequency vibrations that were destroying the turbine mounting bolts. Modern vibration monitoring systems can detect these patterns and trigger automatic shutdowns before catastrophic failure occurs. The gap between what was measured and what was happening represents a fundamental sensor technology limitation that cost lives. This teaches us that monitoring systems must evolve with our understanding of failure modes. Equipment designed in the 1970s may be monitored by sensors designed in the 1970s, but our knowledge of failure mechanisms has advanced. Upgrading monitoring is not optional for aging critical infrastructure. The decision to use Turbine 2 for frequency regulation, despite known vibration issues, was driven by necessity. The Bratskaya fire had created an emergency, but the willingness to accept that risk reflected a broader pattern of operating at the edge of safety margins because stopping production was economically unacceptable. This pattern appears across industries. The pressure to keep operating, to avoid expensive downtime, to meet production targets, can gradually normalize risks that should be unacceptable. The lesson is not that economic considerations are wrong, they are inevitable. The lesson is that the authority to shut down unsafe operations must be insulated from economic pressure, and that safety margins exist to be defended, not negotiated. The loss of all electrical power, including backup systems, meant that safety systems that could have limited the damage failed simultaneously. The automatic intake gates, the turbine governors, the monitoring systems, all depended on the same electrical infrastructure that was destroyed in the initial failure. Defense in depth means that safety systems should not share common failure modes. This lesson applies beyond hydropower, in nuclear plants, in chemical facilities, in aviation, anywhere that multiple systems are expected to provide redundant protection. Hydroelectric power provides roughly 16% of global electricity generation and represents one of the largest sources of renewable energy. Many of the world's largest dams and hydropower facilities were built in the 1960s and 1970s and are now approaching or exceeding their design lifetimes. The lessons from Sayano Shushenskaya are not historical, they are urgent and ongoing. As we build new renewable energy infrastructure and extend the life of existing facilities, the balance between economic pressure and safety margins will continue to be tested. The disaster at Sayano Shushenskaya reminds us that this balance can fail catastrophically when we lose sight of the physical reality underneath the operational pressures.
The rebuilding of Sayano Shushenskaya became a comprehensive modernization that addressed the specific failures that caused the disaster. Vibration monitoring systems. International standard vibration monitoring systems were installed on all turbines, capable of detecting high-frequency vibrations and automatically shutting down units before critical damage occurs. These systems represent a fundamental upgrade in the plant's ability to detect impending failures before they become catastrophic. Turbine replacement and component strengthening. All 10 turbines were completely replaced with modern designs, featuring enhanced anchoring systems and materials better suited to resist fatigue. The new turbines incorporate lessons learned from the forensic analysis of the failed components, particularly in the design of mounting systems and cover bolt assemblies. Electrical system independence. The electrical infrastructure was redesigned to prevent common mode failures. Backup power systems were separated from primary systems to ensure that a failure in the turbine hall cannot disable safety shutdown capabilities. 16 new power transformers and 10 generator circuit breakers were installed, with improved protection against cascade failures. Emergency spillway capacity. A new shore spillway was constructed to provide additional capacity for controlled water release during flooding or emergency conditions, reducing dependence on the turbines for water management and providing defense in depth against dam overtopping scenarios. Operational constraints and procedures. Formal operational constraints were established regarding turbine usage in rough zones, particularly for units approaching end of design life. Automatic control systems were reprogrammed to avoid or minimize time spent in high vibration power ranges, and manual override authority was strengthened to allow operators to refuse unsafe operational demands. Modern relevance and remaining risk. The rebuilt Sayano Shushenskaya returned to full capacity in November 2014 and has operated safely since then. However, the fundamental challenge remains across the hydropower industry globally. Hundreds of large dams built in the mid-20th century are now aging.
many face the same pressures that led to the disaster: economic necessity, deferred maintenance, and the gradual normalization of operating with reduced margins. The changes at Sayano Shushenskaya demonstrate that the technical problems are solvable, but they require sustained investment and the willingness to prioritize safety over short-term economic optimization. The question is whether other facilities will make these investments proactively, or whether more disasters will be required to force the same lessons to be learned again. 75 people died at Sayano Shushenskaya on August 17, 2009. They were not statistics. They were engineers and maintenance workers, technicians and custodians, people investigating problems and people just starting their workday. They had families in Cheryomushki and lives beyond the turbine hall. They died because the system they trusted to be safe was not, because warnings were not heeded, because economic pressures overrode safety margins. The communities surrounding Sayano Shushenskaya carry the weight of this disaster still. Families who lost sons and daughters, sisters and brothers, parents and spouses. A village that had built its identity around the plant and now had to reconcile that pride with profound loss. The rebuilding of the physical plant was completed in 5 years. The rebuilding of trust, of community, of the certainty that people will come home from work, that takes longer. The lessons learned from this disaster are not abstract engineering principles, they are paid for in lives. When we say that vibration monitoring systems must be upgraded, we are saying that 75 people died because the old ones were not good enough. When we say that economic pressure cannot override safety margins, we are saying that 75 people died because production targets mattered more than their lives in the moment that counted. The measure of whether we have truly learned these lessons is not in the technical changes we implement. It is in whether we prevent the next disaster. It is in whether aging infrastructure around the world receives the monitoring, maintenance, and operational constraints it requires. It is in whether we defend safety margins even when it is economically painful to do so. The 75 lives lost at Sayano Shushenskaya cannot be recovered, but they can be remembered through our responsibility to ensure that the systems we build and operate are worthy of the trust placed in them by the people who work there and by the communities that depend on them. That is not redemption. There is no redemption for this kind of loss, but it is purpose, and it is the only way forward that honors what was taken on that August morning in Siberia when the bolts finally broke and the water came through.